I'm Bill Jannen from the Oscar Lab at Stony Brook University, and I'm going to present BetrFS, a file system built using write-optimized indexes, and that performs well on both random and sequential I/O workloads. So first I'll present a problem that's common to many file systems. So this graph shows sequential I/O. We wrote 1 gigabyte file. The raw disk bandwidth is 125 megabytes per second, and ext4 gets 104 megabytes per second. That's pretty good. But with random I/O, ext4 is only able to pull down 1.5 megabytes per second, which leaves a lot of room for improvement. So what's going on here? Well, random write performance is dominated by seeks, and some back-of-the-envelope calculations can kind of illustrate why. If on this disk, an average seek time is 11 milliseconds, and if we assume a seek for every 4K block write, this implies a maximum disk throughput of 0.4 megabytes per second. The previous benchmark, ext4 did better because of locality and intelligent scheduling, but seeking is a problem. So one insight that other designers have had is if you don't want to pay the cost for seeks, then just don't do it. And that's the idea behind log structured file systems. On the one hand, writing data is just an append to the log. But then file blocks can become scattered on disk when you overwrite them. And reading back that data then becomes slow. So logging presents a different point on the trade-off curve between random writes and sequential I/O. The BetrFS goal is to avoid this trade-off completely. We use write-optimized indexes, which are a class of data structures that can rapidly ingest new data and still maintain the logical locality. What we did was we created a schema for laying out that data that allows us to map file system operations to efficient operations in the write-optimized index. And to make this all real, we did it in the kernel. And by doing so, it exposed a lot of opportunities for performance gains that wouldn't otherwise be possible through integration. So there's been previous work that shows that write-optimized indexes can improve the performance of file system operations. The prior works have been in user space. The BetrFS goal is to explore all the ways that write-optimization can be used in a file system. And that means exploring the impact of write optimization on the interaction with the rest of the system. So BetrFS uses b to the epsilon trees as its write optimized index. B to the epsilon trees are an asymptotically optimal key value store. And what that means is they asymptotically dominate log structured merge trees, which is the write optimized index that many people here are already familiar with. In our implementation, we use fractal trees, which are an open source b to the epsilon tree released by Tokutek. I could go into a lot of detail on how b to the epsilon trees work, but for the purpose of this talk, we'll just consider them a black box that lets us do very fast insertions and fast point and range queries. Even if we treat b to the epsilon trees as a black box, we still have to understand how they work operationally. So b to the epsilon trees implement a dictionary on key value pairs. And what that means is we can get, put, and delete elements one at a time, or we can query over a range of values. B to the epsilon trees also provide us a new operation called an upsert, which is key to the performance in BetrFS. I'll get into more details on this later. But these are the operations we have to work with. And next I'm going to show you the performance of these operations so we can examine how they impact the design of BetrFS. So a really important property of b to the epsilon trees is that there is an asymmetry in the cost to perform a search versus an insert. What that means is that queries, point and range, have comparable performance to what we see in a B tree. So with caching, we can do a range query by paying the cost of about 1 seek, and then disk bandwidth to read the data back. And what that amounts to is hundreds of random queries per second. On the other hand, we can do inserts extremely fast, on the order of tens of thousands per second. So this asymmetry is really important, and we should use this knowledge and re-examine the way we think about building the system. To get the best performance, we want to do blind inserts whenever possible. So an insert without first reading the data. So the mechanism we use to do this is the upsert. An upsert is basically the combination of an update and an insert. With an upsert, you specify the key and then a function to apply to the value of that key in the database. So this way it encodes a mutation. So you can do something like increment a reference count, or maybe modify a range of bytes in a string. So upserts are encoded as messages, and they're inserted into the tree, which means we can do many upserts per second, tens of thousands. And upserts also let us defer the expensive cost of the read and do it at a future time. So this is the schema we use to lay out our data in BetrFS. What we do is we maintain two separate b to the epsilon tree indexes. The metadata index maps a full path to a struct stat. The data index maps, for each block, a path concatenated with the block number to the data. So the implications of this are really important to understanding the performance. We can do fast directory scans because it's just a range query over our metadata index. And disk blocks are laid out sequentially on disk. So that's our schema, and this is how we implement file system operations using the b to the epsilon tree primitives on that data. So reads we can implement as a range query, which is efficient because of the locality full path keys provide us. Writes can be an upsert, so we can perform blind writes if necessary. Metadata updates are just an upsert, so things like A-time can actually be done fast. Efficient directory scans can be done with a range query. And then there's other operations. But a really important trade-off that we make for using full path keys is that there are some operations that are tough to implement as just a single b to the epsilon tree operation, and that's where we really suffer. And I'll examine this trade-off more in our performance section. So those are the operations, but by integrating the b to the epsilon tree in the kernel, we had other opportunities to explore the design and the interaction between the randomized index and the infrastructure of the Linux kernel. So one thing we did was we integrated BetrFS with the page cache and basically converted write-back caching to write-through caching. And the reason we did this is because a single byte update to a page in the cache turns into a full page write-back, which incurs write amplification. And by using upserts, we're able to avoid this completely and just encode the data that's changed. So there are three cases I want to walk through to explain how this integration works. We want to write to the file foo.txt, and that page is not cached. All we have to do is insert an upsert and persist that change to disk. No read was required, so we were able to issue a blind write. So no read, modify, write. If, however, our data is cached, what we do is we see the page is there, we check if it's dirty, and since it's not, it's clean, we do an upsert to persist the change to disk, which is quick, and then we update the in-memory state of that page, and we don't have to mark it dirty, because all we've done is bring it up to date with the on-disk representation. The final example can only happen when we have a writable mmap file, and that's when we want to write to a page that's dirty. So if the page is cached and dirty, we just treat it like a normal file system, update the in-memory state, and rely on page write-back to persist the change. In this case, we could do an efficient update with an upsert, but that change would just be overwritten in the future with page write-back, so we avoid that. So some takeaways. By rethinking the interaction between the page cache and the file system, we benefit more than if we just simply sped up the individual operations. So we can use upserts to make blind writes, And we can use upserts to do sub-block writes without the write amplification of full page write back. So that was basically the schema and how we mapped VFS operations to be the epsilon tree operations. And this is how the system looks overall. So BetrFS is written as a kernel module, and it's registered with the VFS like any other file system. But we took the fractal tree implementation from TokuDB, and we took what we needed and ported it into the kernel as a large binary blob. And one of our design goals going in was to change it as little as possible. And what that meant is that we had to use another file system as our block allocation and manager. And we use ext4, but there's no fundamental choice or fundamental reason that we couldn't use another file system. But ext4 performed very well and has not been a bottleneck. Okay, so when evaluating the system, we wanted to answer the following questions. Do we meet our performance goals of speeding up small random writes? Are we competitive for sequential I/O? And are there real-world applications that actually benefit from using our system? So to get this out of the way, our experimental setup, we used just a simple desktop spinning disk. We compared with ButterFS, ext4, XFS, and ZFS. We use default settings for all the file systems, and all the tests I'm going to show you are cold cache, and the error bars represent 95% confidence intervals. Okay, so this graph shows the performance of small random writes in our system. What we did is we wrote a 1 gigabyte file with random data, and then we performed 1,000 random 4-byte writes to that file, followed by a sync, to make sure that all the writes actually made it to disk. So here the y-axis is time, so lower is better. And it's actually a log scale, so keep that in mind. We were able to finish this workload in 0.17 seconds compared to over 10 seconds for the other file systems. So that's over an order of magnitude faster, and that's really significant. And we were able to get this performance because we were able to issue blind writes using upserts. This next workload shows the ability of BetrFS to create many small files and write to them. So what we did is we created 3 million files, writing 200 bytes to each one, and we did it in a balanced directory tree with a fan out of 128 to avoid the pathological case of many files in a single directory. So how to interpret this graph? The y-axis is the rate of creation of files per second, and any individual point is the cumulative throughput at that point in time. So after creating the 1 millionth file, that point represents BetrFS's throughput overall at that time. Okay, so one thing to know, again, it's log scale. So this shows the steady state performance of BetrFS is order of magnitude better. So then we wanted to evaluate our performance on sequential I/O. We wrote a 1 gigabyte file with random data and then read that file back. So for sequential reads, we do well. We still have some work to do. And for writes, we get less than half the bandwidth of other file systems. Part of that reason is because we write all the data twice for full data journaling, but we write it at least twice, and there are some things we have to do to improve this. Don't think that these are fundamental, and we are in the ballpark, so we're happy with this, but we've got a lot of work to do. In the next two slides, we'll examine the trade-off we made between using full path keys for all the blocks in our data store. So this graph shows the time it takes to delete a file. On the y-axis is time, so lower is better, and the x-axis is the size of the file. You can see it's almost a perfectly linear relationship because as the file scales, we have to insert a delete for each block. The same is true for rename. So that's a trade-off we made for using full path keys, is this order n scaling for these operations. But the benefit we get is that directory scans are fast. These two graphs show find and grep from the root of the Linux source tree. Its y-axis is time, so lower is better. And the difference between the two is that find just operates on the metadata, and grep actually examines the data as well. BetrFS does very well because it's able to take advantage of the locality and perform many file system operations as range queries. This next workload shows the dovecot mail server using the maildir mail format. And the workload here is 50% reads and 50% marks or moves. So one thing to note about this workload is it's very sync heavy. And since it's maildir, what this workload basically amounts to is a bunch of operations on small files. So BetrFS is able to achieve good performance, and dovecot realizes gains by using us. The final application I want to show is rsync. So what we did here is we rsynced one directory on a file system to a brand new directory on the same file system. If we didn't use the in-sync flag, what rsync does is an lstat for each file that it's going to create, even though we know that it doesn't exist. By using the in-place flag, BetrFS is able to take advantage of upserts to implement blind writes, and it achieves very high throughput. So that's the performance I'm going to show now. We have more experiments in the paper, but let's re-examine the questions we set out to answer. So the question, do we meet performance goals for small random writes? Yes, we get over an order of magnitude improvement on the benchmarks here. As far as competitive I/O, we're kind of competitive. We have some work to do, but we're in the ballpark. And there are definitely real-world applications that benefit from BetrFS. Now, not all applications will benefit, obviously. Those that do deletes or sequential I/O might be a little slower, but definitely there's a class of applications that will see real gains. Okay, so that's BetrFS. We've shown that you can have your cake and eat it too. There are files, we can design a file system that has good sequential and random I/O performance. We've examined what read-write asymmetry can mean, and the performance of a write-optimized index requires revisiting many of the design decisions deeply embedded in file system design, like do we want to use inodes, the difference between write-through and write-back caching and those implications. And we really want to build our applications and design our systems so that we can take advantage of blind writes whenever possible. So our code is available on BetrFS.org, and at this point I'd be happy to take your questions.
Hi, I have a question and also an announcement. I'll get the announcement out of the way first.
Sure.
So the announcement is for people to remember for tomorrow. The first and only showing of the imitation game will be at 8:30, not 9 o'clock. And if you're presenting in that session, please come a few minutes earlier, test out your system, and talk to me. Now the question. I was wondering if you can comment on the upserts. If you have all these blind writes and you have different things that happen at different times and possibly conflict over the same ranges, is your system just sort of queuing them up and keeping track of them to avoid conflicts?
So I want to make sure I understand your question. So are you talking about conflicts in terms of ordering or that overlapping upserts?
Both.
Okay, so in terms of overlapping upserts, to answer this question fully would require more explanation of the data structure, but to give you an intuition, they basically reside in the tree, and to do a read, we have to do a full root to leaf traversal to get the value, and we assemble all the upserts and apply them in order to the value. So does that answer the question?
I think so.
Okay.
Yeah, so I had the related question to Fred. So what's the fragmentation analogy or aging property of the data structure? How come the data structure doesn't get horrible after a month of use or a year or 2 years of use?
Okay, so it's a tree and the nodes are large. So basically when you have to read a leaf, the cost to read it is the seek, but you get to read the whole leaf at once. So that cost is, the seek is amortized. But the data is keyed by full paths. So as your file system ages, the related blocks to a file are always going to be sequential. The individual nodes. Oh yeah, that would be great. I'd love to talk to that. Fine.
I was wondering why is the sequential I/O performance is like twice as bad? Because you seem to use ext4, so it should be basically the same unless you do something on metadata.
So the sequential I/O performance there, you're talking about the writes?
Yes. Mm-hmm.
Okay, so we do full data journaling. So we do write all the data twice. But also the fractal tree is an on-disk data structure, and there is extra writes that could happen as the data percolates through the tree. But we suspect, and we're looking into this, that the high order issue there is the journaling.
Brandon Salmon Tintry, very interesting work. Thank you very much. My question is, this work assumes disk drives with their seek, parameters. How does this change if you're running on an SSD?
Okay, so we've definitely done all our analysis on disks, and SSDs don't have the same seek problem, but there are other characteristics of an SSD that we could speculate about. So the parameters we have to work with here in the B, the epsilon tree are B, which is the block size, and the epsilon, which basically controls the branching factor. So if we, I don't want to speculate too much, but if we can set the block size to match red erase blocks and control the branching factor, that could help with wear leveling and write amplification.
It seems like an interesting thing to look at.
Thank you.
So your ZFS comparison is with checksumming enabled in ZFS, and which algorithm were you using if it was enabled?
So we used the default parameters, but yes, checksumming was, I'm guessing, part of those.
Okay. And do you know if that was the kernel or was that userland or which version? There's a couple different versions of ZFS running around for Linux. Was it fuse-based or?
No, it was not fuse-based.
Okay.
I can get the exact benchmark parameters, and I'd love to talk about this and clear this up.
Yeah.